Hello, we're here to take a look at the Chapter 7 practice test. So we'll go ahead and get started with graphing the exponential function y equals 3 to the x power. So when we're looking at graphing that, one of the things I would do would be to make a table of values. The x values that you want to choose are going to be right around 0. Typically I'll go -2 to 2, and of course eliminate anything that does not really fit. In this case, 3 to the -2 power would be 1/9, 3 to the -1 would be 1/3, 3 to the 0 power is 1, 3 to the first power is 3, and 3 to the second power is 9. That should be sufficient as it takes me right to the edge of my graph. I zoom in a bit more and plot these a little bit. So plotting those points, so -2 is 1/9, so pretty close to the x-axis there. -1 is 1/3, we'll try to have it a little bit higher. 0, 1, should be able to get that there, 1, 3, and then 2 was 9. So there are the specific points that I would be looking for. Remember, with these exponential functions, there are arrows on both ends, and they have this kind of curve to them. So that would be what I would draw for the graph. And then we also have to look at the domain, range, and asymptote for this. Domain for exponential functions is always going to be all real numbers. The range is, however, going to be limited. Notice where the graph is. Those y values are all greater than 0. It doesn't quite get to 0, and it certainly never becomes negative. The asymptote is really right at that same line. It's the horizontal line y equals 0. Remember, that asymptote is the line that the graph approaches as you move away from the origin. And remember, these exponential functions, they will never actually cross their asymptotes. Some functions will, but not these. So that's number 1. We'll take a look at number 2 with the 4 times 1/2 to the x power. I'll make my table over here. Now at the base of a half, I did anticipate using a value like a -3. And notice in my table, it's just the 1/2 to the x power, and we'll take care of the 4 once we have our points. 1/2 to the -3rd power would give us 8. 1/2 to the -2 would give us 4. And then we get 2, 1, 1/2, and 1/4. So those would be the points that I would start with. Again, I would X those in because they are not my final points. So if I zoom in here, so I can do a little better job. So -3, 8 would be about there. -2 was 4. -1 was 2. 0 was 1. 1 was 1/2, and 2 was 1/4. Now, because of the 4 that we have here, again, that will stretch these by a factor of 4. So really we multiply each of those by 4, and if you wanted to even put in an extra column in your table, you could. Now that would bring this up to 32 and this up to 16, so those will not really be plottable points anymore. We get 8, 4, 2, and 1 also. So those would be the points then that we would really get at, and again really being these when it's all said and done. So if I zoom back in a little bit, -1 gives us 8. Put this in blue. So -1 is 8. 0 becomes 4. 1 goes to 2 now, and 2 goes to 1. Again, the graph will approach the x-axis, and there we go. So that's what I would be looking for on the graph. You don't necessarily need the x'd-in points, but certainly I'd be looking for those 4 nice points that we have there. So yeah, again, domain, range, and asymptote for this one. And it can be a little confusing once we start to think of logarithmic functions as well. But again, exponential functions, the domain is all real numbers. The range is what is limited. We have y is greater than 0 again, and the asymptote is y equals 0. So we'll move on to problem number 3. So finding the percent of annual increase or decrease that that model shows. And again, remember our actual model is a times 1 plus r to the t power, where r is that annual percent of increase. That's what we're looking at there. R is the annual percent of increase. Well, 2.3 equals 1 plus R. So if we solve that, we get R has to equal 1.3. Now in terms of percentage of increase, that would be a 130% increase. So that's what we're looking at there. So be careful with that one. Sometimes very easy to make a mistake on that. Alright, so number 4 is our modeling question where we are not necessarily told the rate of change, but we are given 2 consecutive years of numbers. So we have in 2015, the Ewok population is 3,000, and in 2016, the Ewok population decreases to 2,865. Now we are going to make some assumptions. We're going to assume that the pattern is exponential and that it will continue. So what we want to do is write a model for the situation. We'll put that here. And use the model to predict the Ewok population in the year 2020. So we'll take a look at doing that. So one of the first things we need to do is figure out our model. So just like we have our model here, this is the model we'll use for the Ewok population. Now our initial amount will have 2015 really be our year 0. So our initial amount will be 3,000. The other part of that model that we need is we need the 1 plus R. Now a while ago we looked at a formula for figuring out R. R equals the new number minus the old number divided by the old number. And that formula works just fine. However, if I want to find 1 plus R, then 1 plus R will equal just the new number divided by the old number. So a bit easier, I think, to figure that out. In this case, the new number is 2,865, and the old number was 3,000. So we can figure out our value from that. And that equals exactly 0.955. I suppose I didn't really leave myself much room to write my function there. So I'll use purple for my function. So I have my starting value is 3,000. And then I have my decay factor, really, is the 0.955. And then to the t power is what we're looking at. So that's our model. And the last thing we're looking at is to figure out the population in the year 2020. So if 2015 is year 0, then we subtract 2015 from the year in order to get the value for t. So 2020, so 2020 minus 2015 would equal 5, and you all knew that, I'm sure. But I'll plug in a 5 to figure out into our formula to figure out the prediction. So I'll go right in here for t, and then we'll see how many Ewots are left in 2020. And to the nearest Ewok, I come up with 2,383 Ewoks. And so that's how that works out for us. Alright, for number 5, we've got another graph. So again, we'll want to set up a table. And I'll do a table for probably the entire 5 times 2 to the x. Then we'll just shift those values up 2. And one thing I might do too right away here is, since the graph is going to be shifted up 2, I might just try to dash in a line at y equals 2 so that I can, again, remember not to have my graph go below that line. And I did decide to start at x of a -3 because I knew that would be 1/8, and so that would give me a 5/8 for the 5 times 2 to the x. -2, well, 2 to the -2 is 1/4, so we get 5/4 there. We get 5 halves here, and we would have 5 and 10. And then I included the 2 on there, but more just to show that we're not going to actually use that point, because 2 to the second, of course, is 4, and so then we get 20. Notice how all of my values do double as we go through that table: 5/8, 5/4, 5 halves, 5, 10, and then 20. Now, those I will X in to my graph here. I think I'll use purple for that. So -3 was 5/8, so a little over half. I think I'll zoom in a bit, get a better shot at that. -2 gave 5/4, so 1 1/4 really. So about there. -1 was 5/2, so that's really 2 1/2. 0 gives 5, so that's right here. And then 1 was 10, so that's there. Now that's the last point that's really going to fit on there. And then what I'll do to actually graph those is I'll shift those up 2. I'll put that in blue. So we come up 2 from each of these points. Oops. So up 2. So we're here, and up here, and then up 2 more. Now this one's going to be off the graph. I might, guess it's going to be around here or so. And then if we draw a line through there, again, arrows on both sides, just try and hit those blue points. And so there we go. That's what that graph would end up looking like for that one. And again, notice it follows that asymptote at y equals 2 right there. Alright, so here we have a table for number 6. Again, looking at those different x values, and I'm going to make the table including the -4. Again, that's going to reflect the graph over the x-axis and stretch it by a factor of 4. So plugging the -2 in, that would give me 1/2 to the -2, which is 4. Now times the -4 would be a -16. So again, a point that we're not really going to be able to use. The 1/2 to the -1 would be 2, so we'd get a -8. 1/2 to the 0 is 1, so we get a -4. 1/2 to the first is a half, so -4 times 1/2 would be -2. And then we'd be looking at -1 and ending up at -1/2. Now, with all of that, again, that includes the -4, but it does not include the +4 that we have here. So for that, again, notice that is in the exponent with the x, so that is a horizontal shift. So after we plot these points, we'll be moving those left 4. We still will have a horizontal asymptote at 0. Let's see, so the -2, -16 I cannot plot. We'll zoom in a little bit here. So -1 gives me a -8, so I'll X this in here because it's not a final point. 0 was -4, 1 was -2, 2 was -1, and 3 was a -1/2. So each of those points, again, will get shifted left 4 because the x plus 4, which is the exponent. And so just pulling each of those left 4 brings us to these purple points. And there. So there that is. Again, arrows on both ends of an exponential function, so the graph would look like that. So again, you create the table, you draw your points, and again, shift those around if needed, and a nice curve through there with arrows on both ends. Alright, number 7, notice that that is a continuously compounded interest problem. So the formula we use will include the number e. And so we just need to fill in the values that we know. So it looks like we invested $1,600. So that is the p value. Annual interest rate of 4.6%. So make sure, again, that you use the proper decimal there, 0.046. And then how much will be in the account after 4 years. So this is how we would find the value in that account after 4 years. And being a money question, specifically even an investment one, we'll round to the nearest cent. Again, it's not really an approximation, since this is what you would actually end up taking home at the end of that 4 years if you were to do that. Number 8, how much money invested at 5% compounded continuously for 3 years will yield $820. So now they give us the yield of $820. We don't know how much the initial investment is. We do know the interest rate and the time, and so we're trying to solve for the initial investment. And so really dividing both sides by that e to the 0.05 times 3. Be very careful about rounding before you're actually done with this question. If you do that, you're going to introduce some extra error into the process. So what we really want to do is divide both sides by the e to the 0.05 times 3. That will give us p. But again, resist the urge to approximate that value for e. And let's see what we come up with here. And to the nearest cent, I come up with $688.57. Now again, this really is an approximation. If you did $688.56, you might end up a little bit short. 688.57 again is rounding up. So to the nearest cent, that's what you would have to do. Let's see, 9, 10, we are just switching these to log form. So again, good practice for everyone. Remember, the base stays the same. Log base 2 of 32 is 5. And if these are completely numeric, again, feel free to use the calculator to check. Of course, your calculator will confirm that log base 2 of 32 is 5. Likewise, if you do log base 125 of 625, your calculator will tell you that that is 4/3. So that's what we're looking at there. And then 11 and 12, trying to evaluate the logarithms. So again, for 11, we're trying to figure 5 to what power gives us 1 over 625. The thing is, we know 5 to the 4th power is 625. So 5 to the negative 4th power would be 1 over 625. So this really equals negative 4. And again, we could use the same base approach here. 5 to the x equals 5 to the negative 4th. And so then that log has to equal negative 4. Here, remember, this is really a base 10. Tried to draw that 10 in there, kind of failed. So base 10 for that logarithm. So then this is really saying 10 to what power gives us 0.01, which is also known as 1/100th. And 1/100th is 10 to the negative 2nd power. So this logarithm equals negative 2. Again, where this one equaled negative 4. Alright, so looking at graphing these logarithm problems. So number 13, we've got a log base 3 of x. And so when we make our table of values, we want to pick values of x that are really powers of 3. So 1/9 is 3 to the negative 2. So our y value then is negative 2. 1/3 is 3 to the negative 1. So we get a y value of negative 1. 1 is really 3 to the 0 power. 3 is 3 to the 1st, and 9 is 3 to the 2nd. So those would be the points that I would use, and again, that pretty well takes us to the edge of our graph. I'll zoom in a little bit here so I can plot the points a bit better. Let's see, so 1/9 gives me negative 2, and these are my final points, but I might just use x's because it's a little easier to put on my graph here. 1/3 was negative 1. 1 gives me 0, 3 is 1, and 9 gives me 2. So you can draw a curve through those points, arrows on both ends. Now remember, with a logarithmic function, it is the domain that is limited. The x values, in this case, have to be greater than 0. The range is all real numbers, and the asymptote, again, looks very similar to the domain. It's x equals 0. So that's what we're looking at for log base 3 of x. Heading over here, we'll take a look at number 14. Now this logarithm, again, does not have a base, so it's really a base 10. And we have some transformations there. Now with those transformations, it'll take the parent function left 1 and down 3. So again, what I would do is just make a table for the parent function and then do those transformations. And with a base of 10, there's not a lot we can do. So 1/10 would give us -1, 1 would be 0, 10 would be 1, we'd have to go all the way over to 100 to get up to 2. So we want to be careful with that, make sure that we don't do anything that we shouldn't be here. So again, I will X those points in, and these are not my final points. But again, I'll use X's there on these. So 1/10 was -1, so about there. 1 was 0, and then have to go all the way over to 10 to get to 1. Now as far as, again, moving those, we're going left 1 and down 3 from where we are. So I'll use purple here. So left 1 and down 3 would put us here, and left 1 down 3 would put us there. So we want to draw our curve through the purple X's. Now notice as well that, again, we do actually have a vertical asymptote. Alright, so we'll draw our line through those points. Again, arrows at both ends. And there we go. Again, domain, range, and asymptote for this. For log functions, again, these are the ones that do have the limited domain. In this case, x has to be greater than -1. So again, that gets shifted over to -1 because the x plus 1 in the part that's getting logged there, you can see that here. So that pulls the domain left 1. In the range, again, that's all real numbers. And the asymptote, again, is based on the same information as the domain. So x equals -1 for the asymptote there. Alright, so condensing these logarithms down to a single logarithm. So if I try to do just a little bit at a time, I get a log base b of q to the 3rd power plus a log base b of v to the 6th power. And then using the product property to condense that down, I get log base b of q to the 3rd, v to the 6th, and that would condense that down to a single log. Now number 16, I would have a log of x to the 4th minus a log of x plus 2 to the 6th. Now I certainly don't want to take that x plus 2 to the 6th power. That would be kind of a big deal. But I don't have to. I'm just trying to condense this down. So it is a subtraction, so we use the quotient property. The x to the 4th is in the numerator, and the x plus 2 to the 6th is in the denominator. And so it would look like that. And then number 17, we're trying to expand that log. We have really the d and the 12 that are part of that log. So we're going to end up with two logarithms. It will be a difference of those logs, so log base 3 of d minus log base 3 of 12. And then for number 18, the tricky part there is that square root. So a couple ways to do that, but I would probably recommend writing that as a rational exponent and having that both on the 57 and the 74. So that's a log base b of 57 to the 1/2 power over 74 to the 1/2 power. And so I can see when I expand that, I'll expand with both the quotient property and the power property. I end up with 1/2 log base b of 57 minus 1/2 log base b of 74. And if you wanted to, you could factor that 1/2 out. You just then have to remember to have the logs in parentheses then. Right, and number 19, again, they give us a continuously compounded interest problem. Again, they give us the amount that we invest, the interest rate, and here they're not telling us the time. They want us to tell them how long it would take for that account to be worth $500. So if we write out what we know, we want the account to be worth $500. We invest $125 initially, and the interest rate 6.2%. We don't know the time. So we try to solve this one for the power, and then we'll have to use a natural log to actually come up with our time. So we would divide the 500 by 125. And when we do that, we get 4, and that will equal e to the 0.062 times t. Now, we have the power isolated, so we can write this in log form. So since it is a base of e, that would be a natural log of 4 is going to equal the 0.062 times t. So all we have to do is divide by the 0.062, and that will give us our time. So natural log of 4 divided by the 0.062, and we get a time of about 22.36 years. Again, we want to be fairly accurate with this. That is rounded. It says to the nearest 10,000th. I suppose I should do that. So really about 22.3596 years, if I actually round it to the nearest 10,000th like it says to. And again, we want to be accurate there because it is compounded continuously, so you can, again, figure out down to the day about how long that needs to be. Alright, for problem 20, we've got a pack of 950 wolves. We're expecting a decline of 3% annually. Want to figure out how long until there's only 250 members left. So, looking at that 250 being the end result, starting at 950, and a 3% decline would give us a decay factor of 0.97, and we're trying to find that exponent. So really it's an exponential equation. So we're going to have to end up using logarithms to solve it. But before we can do that, we have to isolate the power. So we divide both sides by 250. Now, 250 over 950 is what we get there, 0.977 to the t power. Now, of course, you could leave it as 250 over 950. I would not recommend rounding that. It's not a pretty decimal, but it is actually, rational, obviously. And it does actually reduce down to a pretty nice number. Let's see if we come back up here then. We get 0.97, or do I put 2 sevens there? 0.97 to the t power equals 5/19. So it does reduce nicely, which makes it easier for us to write this in log form. It's a log of 0.97 of 5/19. That's what t is going to equal. And so t ends up being about 43.8291 years. So quite a while, and again that's a long time for a pattern like that to last, but that's what we'd come up with for that problem. Alright, for numbers 21 and 22, we're solving the exponential equation. For 21, we could use the common base approach. That's what I'll show. If you wanted to use logarithms, you could. But again, when it works out to be a nice number, sometimes people have trouble with that log form. The reason the common base works is because 16 and 64 are both powers of 4. 1/16 would be 4 to the negative second, and 64 is 4 to the third. And we take that to the 4x minus 3 power. Now what we end up doing with that is setting the exponent on the left side, the negative 2, equal to the exponent on the right. Now on the right side it would be a power of a power, so we would multiply the 3 by the 4x minus 3, and we end up with 12x minus 9. So from there we just solve that equation. For x, we would add the 9 to both sides. We get 7 equals 12x, so x would equal 7/12. And again, that's the exact answer. Number 22, we cannot use the common base approach because 125 and 150 are not powers of the same base. So we have to use a log equation. And so we switch this to log form. It's ready to go right away. It's a log base 125 of 150 equals 9x minus 2. So we would add 2 to both sides and then divide by 9. So you get log base 125 of 150 plus 2 equals 9x. Divide by 9 and we get log base 125 of 150 plus the 2. It's based on my space here. I'm going to write it as multiplied by 1/9 instead of divided by 9. And that would be what x would equal. And we do want the approximation to the nearest 10,000th as well, so using your calculator you'd figure that out. And to the nearest 10,000th we get approximately 0.3375 as the approximation. Here we're going to solve this log equation. First thing we need to do is isolate the logarithm. So we would divide by 3. We'd get log of 2x equals 4/3. Then we need to switch to exponential form. So we do 10 to the 4/3 power equals 2x. And so then we would divide by 2 to get the x by itself. So 10 to the 4/3 power over 2 is what x will equal. And so that ends up being approximately 10.7722 for that value. For number 24, again we'd have a log here. We would write this in exponential form. So we'd have 10 to the 3rd power equals 4x plus 10. So again, really we just have to isolate the x. So we subtract 10 from both sides. And we could actually figure out that that 10 to the 3rd is 1,000 if we wanted to. It's an easy enough value. And then we get 990 when we take the 10 away. And then we just divide by 4 in order to see what x is. So 990 divided by 4 is what we get for x, and that's 247.5. If you wanted to, also that one's same as 450 over 2, if you prefer a reduced fraction. I don't mind the 247.5 because it is exact, that's not rounded, so I'm perfectly fine with that. For number 25, this log equation, we are going to have to condense this down, and when we condense it we'll be using our quotient property. Get log of x plus 9 over x will equal 3. And then we can switch it to exponential form. We get 10 to the 3rd again equals x plus 9 over x. So that's 1,000 again equals x plus 9 over x. Now, one of the difficult things here is we have an x in the denominator, so we want to get that out of the denominator. The way that we do that is we multiply both sides of the equation by x, and on the right side those x's cancel out. We're left with 1,000 x equals x plus 9. And so what we would do would be to subtract an x from both sides. Again, we're subtracting one x. Sometimes this messes people up here, but it's 999x equals 9. And so we divide by 999. And we get x equals 9 over 999, which of course reduces by a factor of 9. It's 1 over 111, which again would be the exact answer. If it does ask for the rounded answer, I would go ahead and provide it anyway. 0.0090 if we go 4 decimal places. For number 26, we'd have to condense these logs down. For the 2 log of 4, again, that 2 is going to become an exponent on the 4, so that would be a log of 16 minus a log of 3 plus a log of x squared, and that would equal 4. I'm just going to add the 4 over to that side. Now we should be able to condense this down. Let's see, on the top we would have 16 and x squared. On the bottom we'd have a 3. And on the right we'd have that 4 still. Now, in this case, the base of the logarithm is 10 again. So we have 10 to the 4th power equals 16x squared over 3. 10 to the 4th would be 10,000. So we have 10,000 equals 16x squared over 3. So we'd really multiply by 3 and divide by 16. And we actually come up with x squared equals 1875. Now, we would want to go ahead and square root that in order to get our answer. So, and technically when we do that we would get the plus or minus. However, the negative would be extraneous because we're logging an x, so we can't log a negative, so x can't be negative. So this equals, or really, x equals the square root of 1875, which is approximately 43.3013 when we round it to the nearest 10,000th. So here we're condensing this down to a single natural logarithm. We could start with our power property. We'd have natural log of 3 cubed plus natural log of c cubed. 3 cubed is 27. And then we can use our product property. We get the natural log of 27c cubed for that. Let's see, for 28, again, a couple of things with this one. We have the minus the 1/2, and then we've got our quantity there. So a couple different ways you can do that. I think personally I would just distribute that minus 1/2 using just regular multiplication. I'm going to go ahead and condense this natural log of, or 3 natural log of a to be natural log of a cubed. And we'd have a minus 1/2 natural log of b minus 1/2 natural log of c squared. Now using the power property on both of those, I would have minus natural log of b to the 1/2 power, and then minus the natural log of c. Now what happens there is you get a c squared to the 1/2 power, you multiply the 2 by the half, and you get just the 1. To finish condensing this down, we get the natural log of a cubed. The b to the 1/2 would be in the denominator, and the c would be in the denominator. It's not my best half. Let's see if we can make that look a little bit better. And so it would look like that. Now, technically we probably shouldn't have a b to the 1/2 in the denominator, but at this point I'm not too worried about it. I'm just concerned that we can condense that down properly. I'm not going to go back to that and say you need to rationalize the denominator there. Here for 29 and 30 we are solving natural log equations and rounding then if necessary. So again, we'll be looking for both really the exact and approximate answer. Number 29, we are ready to go ahead and switch this to exponential form. In exponential form this would be e to the 8th equals 2x minus 1. So again, just leave the e to the 8th alone for now. We're just going to hang on to that. We'll add 1 to both sides of the equation, and then we will go ahead and divide both sides by 2. So really, the e to the 8th plus 1 over 2 is the exact answer. That's going to be x, and then we will approximate that using the calculator. And when we round to the nearest 10,000th, we get 1,490.9790, really, because it's an 899, so it rounds up. It ends up becoming a 90. So for number 30, we have to condense this down before we can switch it to log form, or sorry, exponential form. So we use our product property to condense that down. We get natural log of 2x equals 5. Switch to exponential form, we get e to the 5th power equals 2x. So all we have to do really is divide the e to the 5th by 2, and that will give us the x. Again, not my best 5 ever. Try that again. So there would be the exact answer, and we'd approximate that on the calculator. And I end up with it's 74.2066 when I round to the nearest 10,000th. Here we're trying to solve the exponential equation, so we have to isolate the power, in this case e to the 4x first. So we'd start by adding 2 to both sides. That gives us 6e to the 4x equals 5. Divide by 6, we get e to the 4x equals 5 over 6. Now we can switch to natural log form, so we get the natural log of 5 over 6 equals 4x. If you think of it as multiplying by 1/4, it'll look a little bit nicer, so we do 1/4 natural log of 5 over 6 equals x. So that would be the exact answer, and we could then approximate that on the calculator. And we end up with a negative 0.0456 when we round to the nearest 10,000th. And then here, this one is ready to be put into the log form right away, so we would do natural log of 1.4 equals 2x. And all we have to do is divide by the 2, so x would equal natural log of 1.4 over 2, or we could do half of natural log of 1.4. And so then that ends up being approximately natural log 1.4 divided by 2, 0.1682 when we're round to the nearest 10,000th. So hopefully that was helpful watching through that. If you have any questions, feel free to ask. And thanks for watching.